Hello and welcome to this vodcast topic D, probably the penultimate vodcast, looking at high level, further aspects of cosmology. So we're in the D4, D5a, the high level sections, and here we are looking in D5.1. We're going to look at the cosmological principle and critical density and the topology of the universe. In terms of the subject guide, we're looking at the cosmological principle, we're going to be looking at a little bit of the cosmic microwave background and redshift, and we're going to be looking at a concept called critical density, which also involves looking at the two equations down there. You can see the skills there on the right. We'll start off with the idea of a cosmological principle, and this is very interesting because it's as much philosophical as it is physical. The basic statement of a cosmological principle is that the distribution of matter in the universe is homogeneous and isotropic. To expand on that, the idea of being homogeneous is that wherever you are in the universe, if you look on a large enough scale, you're going to be able to see the same sort of things. And this is a question of scale. So you're not going to see exactly the same immediate surroundings, but if you look out there into space, you should see approximately the same distribution, the same statistics relating to stars, galaxies. You look back, you'll see the same early history of the universe. Isotropy is even more interesting, which says that the same physical laws apply everywhere in the universe. So the same constants hold to be true, the same universal constants, things like the speed of light or the permittivity of free space, or the half-life of the uranium-235 isotope. And the same laws, the same relations between those constants also are true everywhere in the universe. The astronomer William Keough has an interesting point of view of this. He says that basically the universe is not cheating us. What we see, what we do experiments on, the rules and laws that we uncover or discover are constant. That we can trust the results of our experiments here on Earth are also applicable to the rest of the universe. And he says that the universe isn't cheating on us because it means that the laws of physics have some meaning. In other words, that different laws of physics don't apply elsewhere, which would make a mockery of our attempt to understand them using scientific principles. Not just in space, but obviously in this relativistic universe in time as well. The same physical laws applied in the past, the same physical constants held true in the past and will do in the future than they do now. As we look further in space, as this chart here reminds you, we are looking deep back in time. So this is the cosmological principle, and as I said, it's a matter of a philosophical statement, and there are some arguments against it. I mean, one of the aspects of it is that it's very scale dependent. On a large scale, yes, on a small scale, no. One example of a symmetry breaking within the cosmological principle is the fact that we're here asking a question. To be able to ask the question implies intelligent life, and as far as we know so far, we are the only intelligent life that we have been able to observe, which, even if that doesn't make us unique, it certainly seems to make us very rare. And so this bit of the universe is different to other bits of the universe in that regard. But the riposte to that is that the cosmological principle is about the laws of physics rather than about the presence of certain particular peculiarities such as us. We could also try and test the cosmological principle by sort of doing a map of the universe, seeing what's out there. People have tried to do this. Here is a map of galaxies, as far as we've been able to plot them. You can see sort of some artifacts here relating to distance and space. As you get further distant, the galaxies get rarer, possibly because they're harder to observe, possibly because we're now looking far deep into time. These two arcs here that we can't observe are purely because our ability to observe distant galaxies is limited because these two sectors are blocked by our own galaxy. We can only really have a clear view if you look out of the galactic plane. A related idea, if we're talking about the universe on a large scale, is to ask the question about what shape the universe is. Now, this seems like a meaningless question. The universe is 3D space. How can that have any kind of shape at all? Well, the idea is that if you take the analogy of a flat sheet of paper, which is what these diagrams on the right here kind of do, then all these surfaces are two-dimensional surfaces, but they curve, if you like, through a three-dimensional space. So you have kind of the idea of a flat piece of paper that is just flat, or you could curve it sort of as a saddle sort of nature, or as a spherical nature. And if you were a tiny, tiny ant living on the surface of one of these planes, how would you be able to tell what kind of shape it had? If it was really blown up huge. One way you could do that is by looking at angles of triangles. If you had a sphere, a surface of a sphere, and you drew a triangle on it, then it would have, angles actually greater than 180 degrees. A flat space would have 180 degrees, and a curved space in this way would actually make a triangle that had interior angles less than 180 degrees. Another way to look at it is parallel lines. On a flat space, parallel lines are parallel, and they stay parallel forever. However, on a positively curved, which is what we call this, they don't stay parallel forever. In fact, I think I have this explained here. So yes, positively curved, spherical. Positively curved space has finite size. It's finite volume, it's all enclosed. If you were able to travel in a straight line for far enough, it would come back to your position. And two parallel lines, here they are, here's a sort of equator line, 90 degrees, so they're parallel, but eventually they will meet and in fact cross. That's called de Sitter space by cosmologists. This is anti-de Sitter space, which is negatively curved. And parallel lines there will always diverge. They will always move apart from each other. Only in flat space, or Minkowski space, as we call it, are the lines always parallel. So this is, don't forget, this is a model using 2D surfaces. We live in a 3D universe, but you can imagine the same thing. A 3D universe could be curved. Triangles might not add up to 180 degrees on large enough scales. Parallel lines might not always stay parallel. Whether they do or don't, whether our universe is flat, negatively or positively curved, is related to something called the density parameter. The density parameter is whether the critical density, the stuff that curves space, is mass, because mass exerts gravity. Mass is spread out through space by density. And if there is enough mass in a small enough space, in other words, if there's enough density, the critical density, then that gravity will curl space-time into a positive curvature. If there's not enough, negative curvature. And if there's exactly enough, you'll have flat space-time. So that's the actual observed density, rho, divided by this value of a critical density. So what is the value of a critical density? Well, we can do some simple maths, or relatively simple maths, to actually work out what that critical density is. And we just basically assume the universe is a homogeneous sphere, radius r, total mass m, density rho, and you've got a little galaxy at the end, at the edge of this sphere, moving away from us, as they do with velocity v. We know that velocity v is given by Hubble's constant multiplied by r, so from us, we'll say we're at the centre of this imaginary sphere. That galaxy is at a distance r away. It will have a velocity given by Hubble's constant. And the mass of the gravity that's holding that galaxy back is all the mass within that sphere, which is the volume of the sphere, 4/3 pi r cubed multiplied by the density factor. The sphere will have energy, it will have kinetic energy and potential energy. The kinetic energy is given by half mv squared, and going back to what you remember about gravitational potential, that'll be minus gmm over r. Substitute, replace v with h0r, replace m with 4/3 pi r cubed rho. We get this really interesting long equation here, which we can simplify. Now we say for a flat universe, the total energy will be 0, which means that these two terms will be equal to each other, and we can again compactify and simplify to get a density, critical density. So a flat universe, the density is the critical density. Rearrange this equation, you get the critical density is 3 times the Hubble constant squared divided by 8 pi g. So the critical density is dependent on whatever the expansion rate of our universe is, Hubble's constant, and whatever the strength of the universal gravitational constant is in this universe. Maybe other universes have a different value of big G, but this is ours. And we can work out what that is, and it works out to be about 5 atoms of hydrogen per cubic meter. If we had 4 atoms of hydrogen per cubic meter, then the universe would be open. If it had 6, it would be closed. But 5 would give us a flat universe that seems to be what some evidence suggests. Now, other evidence suggests we live in an accelerating universe, and we've seen that in an earlier topic. But other evidence suggests a flat universe. One thing that the syllabus wants us to make sure we're aware of, and this kind of builds on the earlier topic, is the difference between cosmic scale factor and temperature. I'm not quite sure where it comes in here, but they say it does. The cosmic scale factor, you hopefully remember from earlier work, is kind of the, if we say that now is a value of 1, then in the future, depending on the nature of our universe, how long in the future, we don't know. If it was a very curved universe, maybe never. Maybe it would never reach 2, but it could go from 1 to 2, where everything is twice as far away. And at some point in the past, it was smaller. So as the universe is expanding, everything, including radiation, is expanding, proportional to the cosmic scale factor. So at some point in the future, assuming we're at, say, theta equals omega equals 0, the density factor equals 0, then in some time in the future we will get a cosmic scale factor of 2, which means that the universe will be twice as big, and any radiation in that universe will be stretched twice as much. So its wavelength will be twice as big. The wavelength is proportional to the cosmic scale factor. By Wien's displacement law, wavelength multiplied by temperature is a constant, so therefore rearranging, the temperature is inversely proportional to this wavelength value. And therefore, as the wavelength increases, therefore as the cosmic scale factor increases, the temperature will get less. Or in the past, as R was smaller, the temperature was greater. So the overall temperature of the universe, if you like, the temperature of the cosmic microwave background, is inversely proportional to the cosmic scale factor. Speaking of a cosmic microwave background, that's another way of finding out whether we have a flat universe or not. It's another way of measuring our density compared to the critical density. And the evidence suggests, by sort of drawing triangles on the cosmic microwave background and comparing them to our models, that our universe is flat, very, very flat. So that's one way of finding out the topology of our universe. Another way is to actually measure the stuff that's in our universe and find its density. And there's where we have a problem. But I'll leave that to the next video.